Hello, everyone. Thank you for joining us for the next session of our Python and AI Level Up series on Retrieval Augmented Generation. My name is Anna. I'll be your producer for this session. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenter and moderators to answer. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'd love to turn it over to our speaker for today. Pamela, thanks so much for joining.
Hello, everyone. Welcome to our Python AI series. This is our third session in the series. So welcome to all of you in the chat and also anyone who is watching this recording afterwards. This will be recorded, so you can always look back at it and catch up with anything you missed. So this is a 9-part series that we are putting on. We're on day 3 here, but we've got another 6 sessions coming up because we want to give you all the fundamentals of generative AI with Python so that you can start building all the AI-powered workflows and automation that will make your lives easier, hopefully. So today we are going to be talking about Retrieval Augmented Generation, or RAG. RAG is actually one of my favorite techniques, probably my favorite techniques with AI, and it's really what got me into AI. Because I saw it as a really practical use for LLMs. So I'm really excited everyone's here today for my favorite topic. Welcome, everyone. If you do want to look at the slides, you can download these slides for yourself and reference them. And hey, if you're inspired, you can go and teach this yourself in the future. Spread the good word of RAG. So we're going to be talking about, RAG fundamentals. We're going to have code samples that you can even run yourself to see the basics of RAG. We'll also show a few more end-to-end solutions that are deployed to Azure to give you an idea for what a larger RAG solution would look like and give you some more RAG resources at the end. So we won't be able to cover every single RAG topic because RAG is a very, very deep topic when you get into it, but we're trying to give you a really good foundation in RAG so that you can get started with it. So if you do want to follow along, this is the repo we're using today, aka.ms/python-openai-demos. We will post this repo in the chat. So you can go to this repo, and here I've got it open. And when you navigate to it, click on the code button and you'll see the code spaces tab and click create code space on main. So what this does is it opens a GitHub code space, and a GitHub code space is basically VS Code inside your browser with a containerized environment running all the code from this repository. So everything will be set up for you. Python packages should be installed. All the environment variables should be there and just already working. That's the goal, is to try and make it easy for you to get started with these code samples. So here you can see that the code space started up. You can even use Copilot if you want. And so then I will use this code space going forward for all the examples. And when we use it in GitHub code spaces, it uses GitHub models, which are free as long as you have a GitHub account. You can also open this repo locally. If you open it locally, you do need to look at the README to see how to configure it with whatever model host you want to use. So the easiest is to open it in GitHub code spaces. Of course, you can also just watch me go through this. You don't have to follow along. This is just an option we'll give to you to make this more interactive. All right, so why do we even need RAG? What is our motivation for learning about RAG? Well, LLMs are great. They're very powerful. They can generate amazing bits of text, but they have limitations. LLMs are trained on, like a certain part of the internet, a subset of the internet. They're trained at a certain point. and then they don't know anything past that point, right? So like, let's say you're using an LLM, it might have a training cutoff of like December 2023, for example, right? So if you ask it about anything after 2023, it just doesn't know. It has never ever seen anything past that date, right? So this can lead to some bad outputs. So for example, like I was asking, okay, can you write some code using the latest version of a package, a Python package? It doesn't give me the right code because it's only seen what was before its training cutoff, right? And even if it actually had seen some of that new code, there's such a bias in the training data set for the old stuff that even if it has seen a little bit of the new stuff, it's still very likely to give you the old stuff, right? Because it's seen so much of what's been around forever and ever. So this is a general issue, is that it has outdated public knowledge, right? You cannot rely on it fully to be able to give you the most correct and accurate answer. The other big issue is that LLMs just don't know internal knowledge at all, right? If you're trying to ask it information about your internal company information documents, it just doesn't know. It has no idea. It's never seen your internal company documents because they are private, and so it would have never seen it. So these are, two big issues for people trying to ask questions about LLMs and getting results that are inaccurate. So what can we do? How can we get LLMs to know information and be accurate with their answers? There's two main techniques. One of them is fine tuning. That's where you do actually retrain the models. You're retraining certain layers of weights of the models, usually like the outer weights of the model. You're retraining it based off a bunch of new data, right? So you start with the base model, then you have like 200,000 examples of new data, and you train it on the new data. And then that tweaks the weights so that hopefully it has learned that information. It's somewhere in the weights, right? But the thing about fine tuning is that it costs a lot of money and time. You have to put together all that data, then you have to run the fine tuning. That can take like several days to run it. Then now you've got a fine tuned model, and so you can only use that fine tuned model, and so that costs money to run a fine tuned model. So it is possible to do, and there are people that do it, and Azure AI does have a fine tuning offering. So for particular use cases, like for very niche domains, fine tuning might be the approach that they use. But what we find is that most people can instead use RAG, where we're not doing any actual training of the model. We're just giving the model the information on demand, and then it's able to answer the question. So this is much more cost effective, much easier to get started with, and it can be very, very effective. So what is RAG actually, right? So you've actually probably already used RAG in the wild. If you've used any of our Microsoft Copilots, we have many Copilots now. We like to call everything Copilot, a little confusing. But in GitHub Copilot, that does have the ability to search on your code space. So when you are working in your code space and you ask a question about it, it can actually search on your code space and answer questions based off your code space. You can tell because it's saying references, right? The key to something is RAG if you're getting references, footnotes, citations. If you're getting any of those, then it is RAG, because that means it actually looked at information and fed that information to the LLM and answered based off of that information. So that's the key to knowing that it's RAG whenever you see citations. So this one says use 7 references. This one says learn more, and it has a bunch of links. And then this one has citations as well. So you've probably already used some form of RAG, in Copilots, or maybe if ChatGPT was searched on the web. Those are all forms of RAG where it is looking up information to help it answer the question, and then answering the question based off of the information that it finds in some data source. So let's talk about the actual RAG technique. Do a little RAG 101. All right, so let's say we get a question and the user asked, how fast is the Prius 5? It's an electric car, right? So they're asking, maybe like this is, a website for an electric car company or review site, right? So they're asking, how fast is the Prius 5? Now, if we just asked an LLM that, it would only be able to answer based off of what was in its data. And so it would really depend on how accurate its weights happen to be for that information. It's always going to be better to find an authoritative source and answer based off an authoritative source. So what we do is that we take the user's question and we use it to search some data store of information that's authoritative for that kind of knowledge, right? So this could be the web, this could be a relational database, this could be a search engine of some sort, right? We need to search some sort of documents that's going to have that data. And then we get back the data and we get it back in a form that we can send to the LLM, right? So in this case, I'm basically getting back as like a table and say like, okay, this is what I found. I found all these Priuses and here's, the data about it. So we get this data back from the search. And then we send the user's question and the data to the LLM and say, hey, LLM, answer this question based off this data. And so then the LLM will look at that data and will give a nicely worded response. So we're using the LLM for its ability to synthesize information. We are not using the LLM's like knowledge of the world, because we're basically assuming that the LLM doesn't have a good knowledge of the world. We're just using the LLM as something that's able to look at a lot of data, look at a question, and synthesize an answer based off the data. And in fact, LLMs are very good at answer synthesis, right? And so users enjoy using LLMs to get the answers because it's faster than you having to, go and like, imagine when you do a web search, you do a web search for something, you get 10 results, you open up those 10 tabs and you like read through each of the 10 tabs. And then in your head, you have to like synthesize all that information. It's much faster for an LLM to basically open those 10 tabs in its head, look at all the information really quickly and synthesize the answer, right? So we're getting to our answers much more quickly. And that's what's so powerful about RAG, is that we're making it easier for people to get their information. So let's actually see how we can implement this really simple RAG using Python. And we're going to use the OpenAI Python SDK. So this is our first code example. So I'm going over to GitHub code spaces, and I'm going to open up rag_CSV. So we're starting really simple here. Our data source is going to be this CSV file here, right? Typically our data sources would be much, much, much bigger, but we're trying to start simple here and just demonstrate how these things work. So this is a data source that has a bunch of electric car and a bunch of stats. So then we have our Python code here. And at the top, this is all just connecting to an OpenAI model provider. So we're going to be using GitHub. And so it connects to that. And so then we get into the RAG. So let me make this bigger so we can really see what's going on. Let me remove my mini map. Oh, mini map, toggle the mini map. Okay. All right. Make this bigger. Okay. So what we can see is that the first thing we do is read in our data. And then we're creating a tiny little index. I'm using this Python package called Lunar. If you know Solar, it's like a smaller version of Solar, Lunar. But basically, Lunar is just going to do a text search over the data. So I'm making this tiny little search index using Lunar based off the documents in that CSV. So now I've got, basically my database or my search index. I've got something I can search, right? We need something we can search. Then we get the user question. And we use the user question to search that index. And then we get back results from the index, right? And so I think in this case, we get back, I don't know, like 10 results or something like that. So we get back some small amount of results. Then we format that in a way that the LLM will understand. So in this case, I'm using Markdown. You could use JSON. You could use free text. I mean, LLMs understand lots of formats. So, that's just something you can decide. But in this case, I decided to use Markdown since they understand that pretty well. And then I display them. So now I've got my matches. And the next step is to actually send this information to the LLM. So here my system message says, okay, you're a helpful assistant that answers questions about cars based off a data set. You can use the data set to answer the questions. Do not provide any information that is not in the provided sources. This is a really important line to put in your system prompt for RAG. is assuming that you only want your RAG to answer question based off sources. You have to tell it that. Otherwise, it will try to answer based off what's in its weights. So you have to be really explicit to say, hey, you got to stick to the sources and nothing else. So then we send off a request to the LLM. And here, I think I'm using GPT-4o. I'm using a temperature of 0.3. So typically for RAG, I do want a lower temperature. You could even go as low as 0 if you want. But, somewhere between 0 and 0.3, that tends to work fairly well for me. So I send in the system message, I send in the user question, and then I send in the sources. So that is my only request to the LLM. This is my RAG request here. And then I get back a response. So let's actually run this now. Okay. So then we can see these are the results. So it matched it found everything matching Prius. And then we get back the result. The Prius 5 from 2011 has an acceleration time of 9.51 seconds. And it says that represents the time to go from 0 to 60. And we can check and see that that does match what it says in the table. So, it's nice that it can read tables, it can look through tables, and it can get back accurate responses. So this is a really basic RAG flow. Now, I think some people are wondering, like, well, that CSV was really small. Why didn't we just send the entire CSV to the LLM, right? And you totally could do that now because LLMs have very large context windows, which means how much information you could throw at it. And so in this case, with this tiny of a CSV, realistically, we can just send that entire CSV to the LLM, and we don't have to do that first search step. But imagine that this CSV was, 100,000 lines, 200,000 lines, 400,000 lines, right? At that point, we do need a search step. And even if it was, 10,000 lines, and that might fit in the LLM's context window, there's a lot of information that it doesn't need. So even if you can send a lot of information to a model, it doesn't mean you should. It's generally better to cut down the amount of information to only the relevant results for that question and send only that information to the LLM. Because the more information you send to the LLM, the more confused it can get, the more distracted it can get, the more likely you're going to have inaccurate answers. So we're using this retrieval step in order to cut it down and say, like, okay, well, these are the only things you should have to look at. Here's a really limited set of retrieval results. Focus on that and use those to answer the question. Okay, so there we go. That's our basic RAG. And, I see some questions like, okay, do we need to use Markdown? No, you can send your sources as plain text. In this case, I thought a Markdown table was a nice way of displaying it, because also it's just kind of nicer for me to look at than plain text. But, LLMs can parse a lot of different, they can understand a lot of different kinds of formats. So, you can experiment with what works for you. In this case, I decided to format it like this, but LLMs can understand all kinds of things. All right, so that was our basic RAG. So now we're going to get fancier. We're going to make this RAG more and more sophisticated to be able to handle more situations. So the next thing is that a lot of times when we're doing RAG, we're using it for conversational AI. So, like for chatbots, something where you can have a full conversation. So we need to think about what it looks like to have multi-turn support, meaning that we can go back and forth with the LLM, asking more questions, asking follow-up questions, right? So the user asks, oh, how fast is the Prius 5? And then it says, oh, blah, blah, blah. And then I say, okay, well, how fast is the insight, right? So I need to be able to handle that query. And so in this case, like, I could just, I could send all that information to the LLM, and I would send it the full conversation history too when you're doing this multi-turn, because there might be some information from earlier in the conversation that the LLM needs to fully answer a question. Because a lot of times when we ask follow-up questions, we're referencing earlier things, right? And so there we get back an answer. So let's try that one out. So go to RAG multi-turn next. RAG multi-turn. Okay. So the way we're implementing the RAG multi-turn is very similar to before, but now we just have a while loop, and we're asking for the question from the user. And so we get back our results. We send it to the LLM. And then we append the result to the list of messages. And so that then the next time that we send messages, the former answers are in there, right? So we can just test this out and make sure that this works. Okay. So say, okay, how fast is the Prius 5? All right, we got back an answer. And then I say, okay, how fast is the Insight? And we got back an answer there too. So that worked. That actually worked. It got back good, accurate answers both times. However, there are some times where we need to add an additional step when we're doing multi-turn conversation. And so what we're going to add is this step called query rewriting. And the reason that we need to add this step is because a lot of times when there's follow-up questions in a conversation, those questions don't have enough context, right? So here in this conversation, my final question is, what about the insight? And there's two issues with this question. One is that it has a spelling mistake. So ideally, we would fix spelling mistakes before sending it into a search engine. Two, it says, what about the insight? If I just asked you that, like if I just asked you that question with no context and I just said, hey, what about the insight? You'd be like, what about the insight, right? Like that is not a full question. That question only makes sense in the context of the earlier one, right? So ideally our search engine would know, our search step would know that we were asking about the speed of the insight, right? How fast is the insight? So we're going to use a query rewriting phase in order to say, okay, here's the user's question. Here's the past conversation. Can you turn the user's question into a better search query so that we can get better search results for this user question? So what we're going to do is send that full conversation to an LLM and tell the LLM to please rewrite it as a better query. And so in this case, the LLM might rewrite it as insight speed, right? So it's fixed the spelling mistake and it's pulled out the fact that what we care about is speed. So that way you can search through the data sources for speed. Then we use that rewritten query to search the search engine. We get back the results and then send them to the LLM like we did before. But now you can see we actually have two calls to an LLM. The first one for the query rewriting and the second one to actually answer the question. And that the goal of the first one is to really improve the search results so that that search step can get the best results. So let's go ahead and try out our query rewrite. Query, okay. All right, so here with query rewriting, now we actually have two system messages because the first one we need for the query writing. So it's like, okay, your assistant that rewrites questions into good keyword queries. So I gave you some information about what's in the CSV. I said, don't use punctuation, don't use casing, right? This is all depending on the particular search index you're using. In this case, this search index is pretty basic and, I wanted to have a easy formatted query for it. And I said, respond with only suggested keyword query, no other text. Okay, so that is the prompt we're going to send to the LLM when we ask it to do query rewriting. So then I get I get the question. I send that question to the LLM. I say, here's the new user question and here's the history. I get back the suggested query and then I use that in order to search. And then the rest of it is the same as before. So let's try this out. We're going to see what it ends up rewriting. Okay, query rewrite. So I'm going to say, all right, so start with our normal one. How fast is the Prius 5? And it does the rewritten query is Prius 5 acceleration. And that's perfect, right? It got what was most important out of that question. And that's a really good search for this. And now I can say, what about the insight? And I'm going to misspell it on purpose. Okay. All right. And this time, so it rewrote that query as insight. It didn't say insight acceleration. Like ideally it would have done that too. But in this case, it ends up being a good search, right? So insight, and we got back the right results here. And then we could keep going. So that's the goal of the query rewriting step, is to improve the query in order to maximize the search result quality. So then we get back our response and doing well. Okay, so that's showing you our RAG flow with multi-turn support and query writing, and that can get you very far. Now, so far, we've only been working based off of the CSV data, and we need to figure out how can we handle other kinds of data, right? Because for many people, we're doing RAG based off of unstructured documents like PDFs, docx, PowerPoints, right? And that's what's really exciting, is the ability to actually use LLMs to sort through these, vast troves of PDFs that nobody wants to have to look at. So how do we do RAG on PDFs? In order to do that, we first need to ingest the PDFs. That means we need to take the PDFs and turn them into a format that we can actually search. So I'm going to show you one possible ingestion flow that we can use in order to make PDFs more searchable. So we start off with a PDF. Then we need to extract the text from the PDF, right? So in this case, we're going to use PyMu PDF because that's a Python package that we can run locally. We could also use other options, like I usually use Azure Document Intelligence for production. It's very, very good at extracting. You can use any sort of service that knows how to extract the data out. But the point is, you need to extract the text out of the document. Then we want to split that text up into chunks, because we don't want to store the entire document in at a time in the database, because we want to restrict how much we're sending to LLM. Because if you have a 300-page PDF, we don't want to have to send a 300-page PDF to the LLM, right? That's going to take time, that's going to distract the LLM, and it's going to cost money. So we want to split up that PDF into chunks. So you can use a pre-built splitter. LangChain has a really nice splitter that you can use. They've got a couple different splitters. And so that splitter will try to, break up the text based off of the, sentence boundaries inside the text. There's various different types of splitters. And this is like a whole topic. And I'm sure we're going to have lots of questions about that. But you want to split it in some logical way that respects, kind of the flow of the document. Then you want to vectorize the chunks. You want to take each chunk and turn it into a vector embedding. We talked about vector embeddings in yesterday's talk. Hopefully many of you were able to join for that talk. And this is going to allow us to do more powerful semantic search on the data in order to be able to find, the things that really match the user query. So far in the examples I showed, we were just doing a full text search, but it's really more powerful when we can add in a vector search as well. And then finally, we're going to store the chunks in our index, right? So in this case, we're just going to store in JSON because we're just running this locally. Typically, you would use a search service like Azure AI Search, or a database like PostgreSQL, MongoDB, etc. Now, the question I always get is, why do we need the split documents? And we've talked about this already, but right, so LLMs have limited context windows. These days, it's around 128,000 for most of them, which is actually really, really big. But it still is limited. So that's about a 300-page document, depending on how much text is in there. But even so, even if it fits inside there, we want to reduce the distraction. And there's been lots of research showing that when an LLM receives too much information, it gets distracted. It can't find the right information anymore. And there's also just cost and latency, right? If you send a 300-page document, that's going to cost you a lot more money, and it's going to take a lot more time to process, right? So, if you don't have to send it, don't. It's better to chunk it up and just send the relevant chunks and just give it what it needs to answer that information. Now, people ask, how big should the chunk be, right? We did some research. The AI Search team did research a couple of years ago where they found that the optimal size of chunk was 512, and they got the best recall, which means the best search results when they had 512 tokens in the chunk. I have talked to people that are using 1024 and finding that that's working well as well. So, you can experiment for your own domain, but you can read the blog post that we have there to see how they run those experiments, because that also gives you an idea for how you might run similar experiments. But this is what they found, is that at that time with those models, it was 512. I think with the models getting bigger context windows and getting more powerful, people are experimenting with larger chunk sizes like 1024. But that's a rough estimate for you. Now, token sizes do depend on languages. So if you are chunking up languages that are non-English, then the amount of tokens, the amount of actual content that'll fit inside a token is actually smaller. So that's something to keep in mind as well. The other question is, where do you split the chunks, right? Do you split at a token boundary, at a sentence boundary? Do you overlap the chunks? And so what they found was that the best was if they split the chunks at sentence boundaries and then also had overlap between the chunks, right? So that instead of having it just be like this one ended here and this one started there, they would overlap a bit between each of the chunks. So they found the optimal overlap was 25% between chunks. So that's really interesting, and that's something you want to keep in mind with your chunking strategy as well. Also, if you're in your documents, you've got tables, or if you got figures, generally you don't want to split up tables. Like ideally you would keep the tables all in one place. So document ingestion is a huge topic, and but there's tons of good questions. See one about like, oh, how do you ingest videos? That's a great question. I actually haven't personally done that myself. But there's, at least some research that people have done into trying to figure out optimal splitting. And there's packages, libraries that already exist that will do the splitting for you. So I think generally, when possible, use more established techniques in order to do this splitting. All right, so now we're actually going to be able to do this ourselves in Python. So that ingestion flow that I just showed, we're going to do that in Python. So that's in the repo. Let me open it up. All right, so we are ingesting some Wikipedia articles. So I download the Wikipedia articles as PDFs so that I could ingest them. So here we've got the file names of the articles that we're ingesting. It's a bunch of articles about bees, because I love bees. And what we're going to do is for each of them, we're going to use the PyMu PDF for LLM package in order to convert them to Markdown. So we get back the extracted Markdown text. Then we're going to use the recursive character text splitter, which is from LangChain. We're going to use that in order to split them up. And we gave it the chunk size of 500, because remember I said that our research showed that that was about the optimal chunk size. And we also said our chunk overlap here. And we said 125 tokens, because that's about 25%. So that's going to split according to those parameters. And then, right, so I get those documents back out. And now I've got a bunch of chunks. And so I'm going to store each of those chunks and say like, okay, this is the first chunk, second chunk, third chunk of this document. And I'll store that in the JSON. And then for each of the chunks, we create an embedding. Here I'm using text embedding 3 small from OpenAI. Create the embedding and store that inside that chunk data as well. And then finally, we save it to a JSON file. Now, I'm actually not going to run this one because it does take time to do this process, especially the embedding step, because that is a network call to the embedding API. But I will show you, we've already got the chunks ingested here. So I can show you what they look like. We can see here's the ID, here's the text, right? So this is the very top of this particular article. You can see all the, markdown representing the Wikipedia article. And then we can see the embedding, right? So we have a bunch of these, right? So, for a particular PDF, we've got multiple chunks in that PDF. I'm not sure how many chunks it ended up making, quite a few there. And each of those chunks has the text of the chunk and the embedding. All right, so now we've got it ingested. So now the next step is to actually do the RAG on that ingested data. So how are we going to do that RAG? So let's do something similar to what we did before. We'll start off with that. So this is our RAG documents flow.py. So what we're going to do is open up that JSON. And in this case, I'm only doing a text search. I'm using the Lunar again. So that only does keyword search, text search. It doesn't do vector search. So we're not doing vector search yet, but we will get there. So here we're just setting up a keyword search index. Then we get the user's question. We use that to search. We get back the matching documents, and in this case, we just join them with new lines, right? So it'll understand. We do also give it the document ID, right? Because we want it to be able to cite its sources. So when we're doing RAG on documents, we typically want to make sure we're storing the file name, you know, and sending that to the LLM, so the LLM can say like, oh, I found this information in this file. And so then in the system message, this time I say, cite the sources that you use to answer inside square brackets. The sources are in this format. So this is something that you want to do when you're doing RAG on documents to make it really clear where the information came from. And then sending it to the LLM. So let's try that. See, okay, Python RAG documents flow.py. Okay, and we get back a response. So it said retrieved 87 matching documents, only sending the first 5. And I asked the question, what did I ask? Where do digger bees live? They live in dry, hot environments in North America. And here you can see that we do have a citation. So that's great. So that worked. That's what we wanted. We wanted an accurate answer, and we wanted a citation so that we could then, you know, potentially open up the PDF and see where that answer came from. Okay. So that works, except, you know, we're not doing, you know, we're just doing a free text search. So if I asked a different question, like, which bee is cute and gray and fuzzy? I don't know. Let's try this one. Let's see how it does with this one. Cute and gray and fuzzy. And it did actually get it this time. Let me see. Cute, gray, fuzzy insect. I'm trying to come up with a question where it's not going to work unless we bring in vector search. I think it's getting it this time. Cute, gray, fuzzy, cute, fuzzy, cute, fuzzy. Let's see. Try to make it really hard for it. Oh, it got 0 matching documents. Great. So I said cute, fuzzy, and I got 0 matching documents because it couldn't find the term fuzzy anywhere in those documents, when in fact the digger bee is incredibly cute and fuzzy. So if we bring in the vector search, we should hopefully be able to handle the query cute, fuzzy. So how do we bring in vector search? Well, when we bring in vector search, we ideally want to still keep keyword search. So we want to have a full search stack where we have vector search and we have keyword search. We merge the results in, and then we re-rank the results according to the query. This is our complete optimal search stack. And this is what we want to strive for when possible, because the research shows that this will get us the best results. I've got a blog post about it where I ran, you know, I ran my own tests on my own RAG data, but we've also run these same tests across really big data sets as well. And this is the optimal thing, because there are some search queries that vector does really well for. There's some search queries that keyword does really well with. Like if it's an actual like proper word, it's the exact word, keyword search does really well for that. So we ideally want to be able to keep both vector search and keyword search and be able to merge those results together in a meaningful way. So how does this work? So we get the question, cute, gray, fuzzy bee. And we send that question to both keyword search and vector search. And we get back the results, right? So keyword search is going to get back results for B, because that's what it's matching. And then vector search is going to get back results for anything that it thinks are, you know, similar to semantically to that query. And you can see in this case, it actually got an additional one, which was hoverfly. And because it thought that that was a similar result to cute, gray, fuzzy bee, because it actually does, it looks like a bee. A hoverfly mimics a bee. So it you know, it's semantically similar to a bee. It looks like a bee. So then we merge the results. And the way this fusion step works, this uses an algorithm called reciprocal rank fusion. And what it does is it looks to see where the results you know, happened, how they were ranked in each of the subqueries, and says, okay, well, Carpenter bee was #1 in both of them. So that's going to be ranked really highly in the results. Pacific digger bee was #2. That's also high. And then Western honeybee, it sees is 3 and 4. Hoverfly didn't see in keyword search at all. So that should get deprioritized, right? So when it ranks these results, it figures out that, this is the merged results from those subqueries. And then we send to a special model called a re-ranking model that's going to look at the original user question, look at the results, and then do an additional re-ranking step. And so in this case, it would actually switch specific digger bee and carpenter bee, because digger bees are actually, they're cute and gray and fuzzy. They're a much better match for the original question. So the re-ranking model would see that and then switch those two results. So this is our full stack in order to get the best results. So we can actually do this in code. So we've got this implemented in here. So let me open up our hybrid flow. Now, this one, we're going to have to bring in a few more things, right? So we'll see how this works. All right. So our full text search is going to be what we used before, the Lunar, and that's just, basically doing our keyword search using that index. The vector search, this one is using cosine similarity. So here's our cosine similarity function. We talked about this in yesterday's vector embeddings talk, and this is how we're going to measure the distance between the vectors. So what we do is we take the user's query, we convert it using the same embedding model, we get back that embedding, and then we search all of the existing documents in order to find the results. Now, in a real search index, we would use a approximation method so that we didn't have to compute the cosine similarity for every single document, but this is just a example. So we are going to compute it for every single example. So this is an exhaustive vector search. And then we get back the results that have the closest cosine similarities. Then reciprocal rank fusion is going to take the text results and take the vector results. And it just goes through and comes up with scores based off of the position that each result was in the subqueries. So it just comes up with those scores, just using a little bit of little fraction math here, and then ranks according to those scores. So this step here does not use any kind of model. It's just doing straight math based off of the indexes in the results, the positions in the results. Now, the re-ranking step takes in the user query and those merged documents. And this one does use a model. It uses a special ranking model. It's not an LLM. It's a kind of model called a cross-encoding model. Here, I'm bringing one from Hugging Face. There's also ones that you can use in production, deployed, like the Cohere re-ranking models. But this is one that I could run just locally here. And so that re-ranking model is going to look at the query, look at each document, and assign a score to each document based off of how well it thinks each document matches the query. And so this is a model that's specifically tuned for this task. All right, so then finally, what does hybrid search look like? We do a text search, we do a vector search, we merge the results, we re-rank, and we get back those re-rank results. That is our full hybrid search. So now let's actually try it out. Here we go. All right, so we're gonna run this. And remember, we're searching for a cute gray fuzzy bee. Now, the reason I picked gray is because gray, I think in the Wikipedia article, is spelled with an E, right? Because we have two different ways of spelling gray in English. So it's kind of an interesting one to use a vector search for, because the exact term gray might not get matched with a keyword search. All right, so we can see that it's being a little slower. I wonder which step it's on. We should do like let's add in some prints. Print, performing hybrid search. Let's see, print, got back, full text search found. Okay, vector search found. There, okay. All right, here we go. All right, I'm gonna rerun it. It was being a little slow. It was getting caught up on something. It may also be from, because here we're having to load in this model. Okay, so we got farther here. All right. Yeah, so the thing is, this cross-encoder model does take time to load in. All this time here is loading in the cross-encoder model. So certainly when you're doing this in production, you generally want to have a good strategy for using the re-ranking model. That's why I would use a deployed model like the Cohere re-rank model. So you can just do a network request to it. All right, so we got back results, and it's able to figure out that the cute gray fuzzy bee is this one, right? And let's try that query. We can try that query we did before. We just said, what do we say? Cute fuzzy. There we go. And then we'll go run this. So there we have our full hybrid search. And you should be like, here we're doing this example just, in Python, in this local thing. Ooh, I got a bug when I did that. Oh, because it found full text search found 0 results, and I didn't account for that. All right, that's why you should always test things. All right, so if I do cute fuzzy bee, that'll work. Okay. So here we're showing this example in Python using all stuff that's running mostly locally. But you can totally use hybrid search on many different platforms. So you can use it on Postgres, you can use it on AI Search, you could use it on Cosmos DB. Wherever your data is, hopefully you can do a full hybrid search so that you can get the best results. Okay. So, so this is what I was just talking about, is that in reality, you're going to be figuring out what kind of, when you're coming up with your RAG, you're going to think about, okay, what is my data source, right? Are you doing a RAG based off of structured data, relational data, right? Like that's actually stored in a database. So in that case, you need a way to turn your searchable columns into a vector and then to be able to search those rows. And you can do that with most databases these days, right? So if that's what you want to do, if you already have existing data that's relational, you should be able to add on an embedding column and embed your target columns into that embedding column, and then do a vector search on that embedding column with a vector search index. However, if you're doing RAG on documents, then you need to think a lot more about the ingestion process. How are you going to ingest it? How are you going to split it? If it's something tricky like video, images, all that, then you have to consider what it even means. Like, what are you actually going to be storing and reasoning about? So that takes a little more time to figure out and decide what your process is going to be. And then you're going to store those and search those chunks. So that's it. Like, when you're starting off with building RAG, think in terms of your data source types and figuring out what, different components you need in your RAG stack. So now we're going to look at two full solutions for RAG on documents and RAG on data. So starting with RAG on PostgreSQL, because hopefully many of you have some relational data that you're thinking that it would be useful to be able to do a RAG on, right? So how can you do it? So the general idea is that, we get a user's question, and then we search our data using that user's question, find the matching results, and then send that to the LLM, right? And in this case, the results are rows from a database. So we'd be sending back a bunch of rows to the database. This is the simplified version of it. I have an open source template that does a full app that has a React front end and a Python fast API backend that connects to Postgres and does RAG. So I've got that running here, so I can show that to you. So here we go. So I asked best shoe for hiking, and we got back these shoes, and those are based off the database. We can see references, and the references are actually rows from the database. And I can look at the thought process here and see that we started off with the rewriting step. So that's, we talked about rewriting steps. So that one, didn't do much rewriting there. It just said best shoe for hiking. It wasn't a very complex question. Got rid of the question mark. So we do that rewriting step, and then we do a hybrid search. So I'm doing both vector search and text search of this database. So we do that hybrid search, get those results from the database, and then send it to the LLM here, right? And then we're able to get back the answers. So if you want, you can look and see how that is implemented, right? You can look at stuff like how I did the hybrid search, right? So in this case, our searches are actually SQL queries. So I have a vector query, I have a full text query, and then I have a merge query here. I didn't add the re-ranking step to this one yet, so I stopped at the merging, but that worked well enough. The thing about relational data is that it does tend to be cleaner than chunked document data. So sometimes you don't need as fancy of search for relational data because it is already cleaner. Yeah, so this shows you an example of how you could do this on a database and develop a full RAG application on top of the database. So that is RAG on Postgres, and I said it does have a query rewriting in it, and gets back the results. Now we also have RAG on Azure AI Search that we do. This is really what we're going to use when we have documents and they're messy and we want the best search possible. I use AI Search for this solution because AI Search has such good search. It's really good. It's got like the best full text search, the best vector search, the best re-ranking. Like it's just really good. And so if your data is messy, like it's chunk documents, then it helps to use the best search engine that you can. So the general approach here is that I would use the search SDK and say, okay, here's my user question. Please do a search using both the full text and the vector version of that question. Let's get back the results. Let's send that to the LLM, right? So similar to what we've seen before, it's just we're using the search service instead of, a database. So once again, we do have a full end-to-end solution that shows this. And I've got that open over here, right? So here, let me ask a new question, right? So here it is asking questions based off of company documents. So it's searching through, and it's just a fake company. It's searching through a bunch of fake company documents in order to answer the question, and then, hopefully provide citations as well that answer that question. I should have increased my capacity before showing it and not cleared the one before. I also have it running. Let me see if I can just quickly run it locally too. Don't remember if this one is the one I maintain, work on quite a bit. So I've always got different branches open working on new features for it. Let's see. Okay, so I'm not going to run it locally. Oh, and this already answered. All right. So it's also running locally now. But here we have the answer. It's streamed in. We've got like the PDF, and we can open the PDF and actually see where it came from, right? So this is when you're doing RAG on documents, you really want people to be able to follow the sources and be able to see what, see the original document and read through and see where it got the answer. So on this one, if we look at the process that it used, we do the query writing step. So that's this first step where we do query writing. And we get back this suggested new query. We use that one to do a full hybrid search of the search index, and we can see each of them has text chunks. They also have embeddings. I don't show the embeddings because they take up too much space, but they each of them have chunks and embeddings. And then we send those to the LLM and ask it to answer the question. Here's another way of viewing the chunks that it got back. You can see this one also even had a table in it. So we were able to retain the table in this case and actually send that table to the LLM as well. And this one also has support for images and figures. So if there are like pictures in your PDF, we can extract that out, and we can also send those pictures to the backend as well. We're going to talk about that in Tuesday's session, actually. Okay. So RAG AI Search, yeah, this one supports the query writing flow. And I was showing that we had that query writing step. Get back the query, we search with AI Search, and get back the answer. All right, I guess I've been talking a lot. Let me take a little break. Woo! Questions. All right. Hopefully that was enough water to get me through. Oh, and there I also talk about data ingestion, right? So how do we do the data ingestion here? Well, we store our documents in Azure Blob Storage. For each of the documents, we use Azure Document Intelligence to extract the data from the documents. So that's similar to what we use the PyMu PDF in the example, right? So this will take any, like lots of different kinds of documents, and it'll extract the text. It also can extract the figures now. And so that's how we can get back the images too. Then we split the data into chunks. We have our own splitting algorithm that we use in this particular repo because we have just all these custom features we needed to support. So that's just checked into the repo. Then we vectorize the chunks using OpenAI. And then finally, we index them in AI search. So this is what our data ingestion looks like for this. We are going to talk more about this on Tuesday in terms of seeing how it handles images, because it gets a lot more complicated and very interesting. Now, how can you learn more about RAG? I know there's so many cool questions and comments in the chat today, because I'm saying like there's this was just the fundamentals of RAG to give you a basis, but there's so many places that you can take it and really dig deep. So these are the ways to kind of think about the components of your RAG app, right? So how are you going to do ingestion? You're going to, try and pick the different tools you can use in order to extract data from documents when you're doing on unstructured documents. What retriever are you going to use? So, here we saw AI search in Postgres. You could also use Cosmos. You could use Azure SQL. You could use Quadrant. You could use Pinecone. You could use Weaviate. You could use Mongo. You could use Document.db. Like there's so many, anywhere where you have your data, that's what you're going to be retrieving. You could use the web. You can search the web. The web is that's another form of RAG. I didn't talk that much about it today, but in some cases you might want to be searching the web and using a web search API. And then what LLM are you going to use, right? There's so many LLMs out there. These days, in my experience, GPT-5 is the best for RAG. It is the most accurate. It catches the most hallucinations. It gives you the most grounded answers. So generally, that's my preference. But there's many other models you can use. You really want models that are going to give you accurate results, grounded results, that are going to stick to the sources. And then orchestrator, you may want to use an orchestrator in order, like an agent framework, in order to organize your calls more, to give you more options. From Microsoft, we have the new agent framework that you could use in the community. Llama Index is very popular for RAG. LangChain, also very popular for RAG. So those are options you can use. I actually didn't use them for any of the examples I showed you. I just used the OpenAI, low-level SDK, but many people do use orchestration or agent frameworks in order to give them more capabilities. And then there's lots and lots of features you can add to RAG apps, right? So you can add chat history, you could add memory. I saw a discussion of memory. We didn't talk about that today. That's like remembering things over multiple conversations. You could add feedback buttons, so you get feedback about what's working well and not working well. You can add text to speech and speech to text, so you have more modalities for interacting with it. User login, and then once you have user login, you can have permissions based off of user login as to what documents they can see. So data access control. You can let them upload files. All kinds of features you can add to the apps, and actually quite a few of those features are in the one that I just showed. So check that out if you are interested in those other features. We've also given many more talks about RAG, because I'm saying it is such a big topic. So recently, in January, I did a RAG deep dive where I did 11 streams about that RAG repo that I just showed, and really showing all the different features of it. So check out those streams if you want to dig deeper into that. We had RAG Hack, which was a hackathon. That was a few years ago. We had the RAG Time series, and I also had a VS Code video where I built RAG from scratch with Postgres. So lots of other videos about RAG that you can check out. Hopefully I'll do another RAG deep dive in the near future, with some of the more updated things that we've learned about RAG in the last 6 months. I mean, we're learning more about RAG techniques all the time and improving our techniques. So there's always new stuff to learn. And in terms of next steps, that was all I want to talk about for RAG today. And we are going to be talking next week about some fun topics. So we'll have vision models on Tuesday, and that's where we'll talk also about RAG with vision. Then we'll have structured outputs, then AI quality and safety. And so that'll be our next week of topics, which will be pretty fun topics. And we also have office hours on Tuesdays. So we hope you join us in the Discord for those office hours every Tuesdays. We have all of the slides, code samples, and recordings linked from this link here. So you can always catch up on anything that you missed. So there we go. That's what I wanted to cover today. We are at time. but I was told that I could answer some additional questions, that we have some time to answer additional questions if I can manage to sort through the chat and find it. So this is a good time to ask any questions that didn't get covered earlier. I really wasn't able to look at the chat during it. So if you do have any additional questions, I'm happy to try and answer some now. Let's see if I can see them. And thank you everyone for coming. And we'll hope to see you. Hope to see you next week. Let's see, I see some references for different ways of doing document extraction, like dockling. Yeah, so we didn't even show all there's so many different tools now for doing document extraction, right? So we showed 2 of them today. Dockling is another one. I was just talking with Gwen about how we should try out dockling. Another one you might want to check out is Mark It Down. That's also on my list. Mark It Down's from Microsoft, and Mark It Down can process things like PowerPoint, Word, and Excel. So that's another option. So it's just good to have options that are different, like price points, and free is always a really good price point. Generally, it's always like the trade-offs between quality and price. I do think Azure Document Intelligence is really, really good and very high quality, but it does cost money. So it is a cloud service, so it's good to know about other options out there that you can use instead. The one we showed today was the PyMu PDF for LLM. So those are some options for you there. Okay, so now I'm seeing some questions. Let's see, how do you display sources? That's probably the question here. In this case, we are opening up an iframe, and this iframe is rendering the blob that is stored in blob storage. Now, what's important here is that we are not using publicly viewable blob URLs, because that is how you open yourself up to people being able to see your documents. So all of we store them in blob. We actually get them back from blob storage using the SDK, using our credentials, and making sure, because also this app supports data access controls. So if you're logged in, it'll check to make sure you have access to it. So we check all the access controls, make sure you're allowed to see that blob, send back the blob actually as a binary to the front end, and then the front end renders it inside an iframe. So yeah, the short answer is iframe, but it's a bit more interesting than that, because we're not just pointing it at a URL, we're actually passing down the binary that we got back from the blob SDK. Let's see some more questions. RAG for flowcharts. I would probably say that we'd want to use our multimodal technique for that. So I think you should come to the Tuesday session and see if you think that our approach to handling figures in documents would work for RAG for flowcharts. I think it would work because we end up describing the flowcharts, and the description could be good enough. So yeah, I think various of these questions are going to be something we talk about on Tuesday. How do different embedding models affect retrieval accuracy in RAG? Has anyone compared OpenAI embeddings versus local models in practice? Yeah, that's a fantastic question, because there is, like, in this in the RAG Postgres repo, I do support multiple embedding models. And so let me show you my my models here. So on here, you can see what I did. I added 2 different columns, and in the column, I actually say which model it is, because you really want to make sure that you know, if you have an embedding column in your database, make sure you know what model you used and how many dimensions, because you need to exactly match that model, because it doesn't make it. You can't search with a different model if it's not the one you use. So here I've got a column for when I'm using text embedding 3 large from OpenAI. And then I have a column for when I'm using Nomic embed text, which is a model that you can actually just run with Ollama. Like you can see it in my Ollama listing here, right? I only have 2 models locally, and one of them is Nomic Embed Test. So Nomic Embed Text it's a really good model. We'd have to look at the leaderboard for embedding models. I don't know where Nomic Embed Text ranks on here, but we have used it for a lot of our examples, and like anecdotally, it seems like fairly strong. Is it even in this? Did they even run it on here? Why would it not be on here? This is the embedding leaderboard. Nomic. It's weird. Okay, so I don't see it on here, but maybe it just doesn't get added to it for some reason. I haven't actually really used this leaderboard very much. So technically, yeah, the leaderboard ideally would have all this stuff on here. Let me post this in the chat. But you can also run your own comparisons. Someone was asking about benchmarking, retrieval yesterday after the vector search talk. So I found this nice article where somebody did a benchmarking of embedding similarity. And here they were looking at Chrome and UV versus Postgres. But the important thing here is how they did it, right? So what you could do is you could use like text embedding 3 large, right? Which is known to be a very good model. And you could use that, and you could use that for your ground truth and say like, okay, according to text embedding 3 large and exhaustive search, we got these results, right? Then you can also use a column for nomic embedding text and get the results. And then what you're going to do is you can run all these these are all metrics where you can run these metrics. So recall, precision, NDCG, these are all common retrieval metrics, right? So you would then rerun your queries with the other model, and you can see how much do the new results differ from your baseline, right? So I thought this was a nice approach. Nice article here. So it's certainly worth considering what options you have there. Okay, so let's see. So all right, so that was a great question. Okay, this is a great question from Christopher Betts. Is it needed or helpful to add additional metadata for each chunk when ingesting documents, like category, specific subject, or project? Yeah, so this is a great question. And this has different names. Sometimes it's called content stuffing. Sometimes it's called content expansion. And I've talked to some of the folks on the AI search team who think that this is a great idea, and they've seen customers use it. Right. So the idea is that, inside the chunk, right. So here you can see in our chunks, we only have the text, but you could add additional things here. Like you could add like what was the most recent section header on the page, or what was the date of this document, or what's the, what was the file name of this document? Like you could stuff stuff into these chunks. You could also just store them like inside, the chunk itself, and just, right. You could add an additional field, right? Like category, like added, here I have a null, right? But you imagine if you were storing category, in the database with it. The question is whether you want it to get vectorized or not. Like that's the big question, is if you want it to, like, whatever you think it's useful for the vector search to know about it, you're going to have to stuff that into whatever gets embedded, right? So like when I was doing the, so here for the Postgres one, I have a specific function that I call toString for embedding that only pulls in the things that I actually think are useful for the embedding model. Because embedding models, they're great at searching free text, results. They're not great at like searching like price. Like I didn't include price in there because I was like, vector search is not what I want to use for price, right? Like I have other ways of dealing with price, but I don't want to put price in a vector embedding because it's not going to work out well with how vector search works, right? So I really emphasized in here, I only put the things that are basically like human text, words, that sort of thing. And I left out things that were more like numeric or were exact keywords like brand, right? So that's something you want to think about, is that, when you're adding additional data to a chunk, like additional metadata, which of that do you actually want to have be searchable, and do you want it searchable via the vector search as well, right? And you can make different decisions, like because you can store something different in your vector embeddings, like you get to decide what you make the embedding off of, right? So you can decide your vector embedding is only going to have the main data, and you could still also, but you could put the additional metadata inside what gets searched by free text, right? So you have lots of different decisions there. But definitely I've talked to people who say that is a good approach. All right, let's see. I had a question. Does it support MP4 to text? I have never done MP4 to text. Actually, currently I'm trying to build an agent that turns these YouTube videos into articles, and that's super interesting. But that one I'm using the YouTube transcripts because YouTube already has transcripts. So I haven't had to deal with MP4 to text. I'm sure there is a Python package out there that would do MP4 to text, and that would be fun. Let's see. Will we talk more about agent framework in a later presentation? Yes, for the agents talk, we are going to be showing a bunch of agent framework demos for that talk. Probably also showing some LangChain because there's a lot of requests and interest in LangChain. Fortunately, agent framework and LangChain, the code that we'll be showing actually looks really similar. So we'll be able to hopefully show both of them in the agents talk in our final week. Okay, in terms of reproducibility, how can we ensure RAG experiments remain consistent across different platforms like Azure AI Studio or local Python environments? Yeah, it's a good question about consistency because, we've talked about LLMs, determinism, right? Generally, you should get the same results from searches. I say this, but actually I spent like last week, hours debugging why my vector search in Postgres was different across 2 different Postgres databases. So, all right. So yeah. So where do we have determinism? Searching, I do find generally like with Azure AI Search, like I if I send in the same query, I tend to get the same results. I have had some issues with Postgres with vector search because here's the thing: anytime you're using an approximation algorithm, especially with Postgres and PG vector, like the rows return does depend on like how the indexes are set up and like when they indexed and what filters you set in and stuff like that. So whenever you're using any sort of approximation algorithm, you risk like something about the approximation algorithm being different. So I have seen some non-determinism, some variance. I'll say some variance in Postgres PG vector with the with the vector search indexes. So that can be that's a bit tricky. And with AI search, I haven't seen that variance. It's pretty reliable when I'm just doing a vector hybrid search. The big variance does come in the LLM. So there you want to really keep track of what model you're using and keeping that consistent. What you can do is set the seed, right? You can see in here, actually you can't see it. It's underneath your question here. Let me raise it up. All right, seed, it says seed. Seed is a parameter we can send to the OpenAI LLMs in order to make them more consistent. So whenever I'm doing evaluations and I'm trying to get similar results, I do set the seed so that I can have more reproducibility across it. It still is not perfect. You can still get variance with LLMs. I think we talked about this on Tuesday. Because of how hardware works and floating point operations and all the different steps involved in an LLM answering a question, you can get variance even if you set the seed. But certainly setting the seed helps. So yeah, you keep as much constant as you can. And, I think it's easier if everything you do is in code. If you're using a low code environment like Azure AI Studio or Copilot Studio, I have a hard time with that because I don't know what they're doing behind the scenes. And so it's so hard to know what parameters they're actually using. So I do think it's really hard to keep things consistent across a low code environment and a high code environment, but within at least a Python environment, then you can keep track of, what model am I using, what temperature, what seed, what are all the settings I'm using, and just keeping that really constant. I do have like evals that I run inside inside this one, and in the evals, I always keep track of right. This is like my configuration for the evals, and like okay, so these are the parameters that I'm using, and I always keep track of exactly which parameters I am using, so that I can have consistency across the evals. All right. Let's see. let's see. When using Azure AI Search with OpenAI, how do you decide what context to feed the model for optimal results? Well, we get back the search results, and then sometimes we can filter based off re-ranker score. So a nice best practice is to set like a minimum re-ranker score of like 1.8. Because usually anything lower than 1.8 is not going to be a good result, right? So usually I'll filter out things that are less than that. Here, the re-ranker scores are quite high. They're between 0 and 4. 4 is really good. 3 is quite good as well. 2 is, and 1 is quite bad. But here, these are all really good. So, we get back results, and, we just send those results as long as they have a high enough re-ranker score. In this case, I only am retrieving 3, but I'm probably going to increase this default going forward because now our LLMs have larger context models. So as long as you're setting a re-ranker score, and you could be like maybe more aggressive with it, with Azure AI Search, you can retrieve more results. The risk is if you retrieve more results, and then you have this risk of adding distracting results there, right? The more you add, the more distraction you can add, and the more likely it can be inaccurate, led astray. So you have this balance between wanting comprehensive answers and between wanting, accurate answers that don't have distractions in it. But a nice best practice is like, okay, we're going to retrieve a bunch of results, but we are going to have a minimum re-ranker score. So if anything is like really irrelevant, we're just going to drop it, right? Now, so we can rerun it. This will probably take a little bit longer this time because we're retrieving a few more results. So we'll just make sure that all the results are relevant enough in order to send. So that is my best practice there. The question, how to analyze RAG result quality. I had a whole live stream about that, but let me see if I have my evals running here so I can show you. Let's see. Let me go into my eval environment here. Got a different environment for evals. Okay. And evaluate. All right. So I'm just going to show you the results of the evals. Let's see if this is running right now. So basically what I do is that I have a bunch of ground truth for this, for this particular data set. So I've got like, let's see what my ground truth looks like. Ground truth is here. Okay, so my ground truth is a bunch of questions and answers, right? So we've got 50 questions and answers here. And, the goal is to show the kind of questions that people might actually answer and to say like, okay, if a user asks this would be the ideal question. And here's the result. So that's my ground truth. And then what I do is whenever I'm making a big change, like changing the prompt or changing the model, especially changing the model, because that makes the biggest effect, I run an evaluation, which means I send each of these questions to the current app and I measure different metrics. And so some of these metrics are using an LLM as a judge, which is using the Azure AI Evaluation SDK. And then some of these are, stuff like latency, that's just a number. The length of the answer, that's just a number. I also do a little bit of regular expressions as well to check to see if the citations match, right? Because if my ground truth has this citation, then the new answer should also have this citation, right? So I run all those metrics and then I store all those evaluations so I can see, like, for example, GPT-5. Remember I was saying GPT-5? GPT-5 is real nice, right? Look at this. We got a 1.0 for groundedness. So according to that LLM as a judge, it thinks that GPT-5 did really, really well at groundedness. And that's one of our top metrics that we care about, which is, are the answers grounded in the sources? So every time there's a big change, a big model, I run the evals and look at all the metrics. And then I'll usually do a little deep dive into the actual answers and see how the answers changed. That is the short version. There is like a whole hour-long stream where I talk about this. So you can check that out in the RAG Deep Dive series. Let's see. If you want structured if you want to structure your output, well, we are talking about structured outputs next week. So definitely come to that one. Oh, and Gwen talked about that. Okay. Should RAG or something else be used to summarize content, like an uploaded PDF to summarize 300 pages to 2 pages? Ooh, that's a good question, right? So 300 pages to 2 pages. So in this case, you wouldn't be doing RAG because you need that entire content, right? If you are summarizing 300 pages of information, you need all those informations. So I wouldn't use RAG in this case. What I would potentially do is consider breaking the task up, because the only thing is, like, you can actually, like, 300 pages is like just on the limit of 128,000 tokens. I know, because I uploaded the 300-page doc to ChatGPT. So in theory, you might be able to actually send all 300 pages to an LLM and get back an answer. But you do have this risk that, one, it might be over the context window, but two, it's 300 pages. It's probably gonna kind of skimp on things and kind of miss some things, right? So what I would probably do is you could use basically like semantic splitting and say, like, all right, let's split those 300 pages up into like chapters and sections, right? And then send each of those sections off to get summarized, right? And so then you can imagine like a flow, right? You have the 300 pages, you split them with chapter sections. So then you have like chapter summary, chapter summary, chapter summary, chapter summary. And then you have the chapter summaries. Then you send each of the chapter summaries off to get summarized. And then you end up having, at the end, you have like the full summary. So I think I've even talked to somebody who's done this exact flow, like to basically like, incrementally like do, summarize as you go along, and so that you finally get the big summary. And so the goal there is that would be more accurate than if you just threw the whole thing. Now you could try throwing the whole thing at it, and you could compare and see what the accuracy is like, and see if it works. But that's what I would think would be the best approach there. Suggestions. What suggestions do I have to minimize the Azure AI search costs? Yeah, that's a good question. Because one issue with Azure AI is that it costs money. I do have like a guide here about, at least for the RagChat repo, how to deploy with minimal costs. And for AI search, I think I talked about turning off vector search, but also for AI search, they do have a free tier, but you're only allowed one free search service across the regions. And that free tier does not support the semantic ranker. And I just told you how great the semantic ranker is. However, if you're trying to minimize costs, that is an option. That's something you can try. The other big thing you can do is with your vectors is that you can compress the vectors, right? So that would save you on storage costs when you compress the vectors. I was talking about that yesterday with the vector compression. And this repo does it by default, where we do the binary quantization and the dimension reduction and the oversampling, right? So that's how you could save on storage costs if what you were spending money on was lots of vector storage, but you might just be spending money on just the base service. In that case, you can play around with the free tier and with disabling semantic ranker and see if your relevance is still good enough. Let's see. Okay. All right. So we should wrap. I've been told we should wrap up soon. And so many great questions here. Oh, I see. Evaluation RAG tools as Ragus. Yeah. So I actually do use Ragus in this repo. It's how I evaluate. It's how I generate the ground truth. It's not how I evaluate the answers. I use Azure AI evaluation for that. But for the generation, I am using Ragus here, which is fun. All right. Okay. So we had lots of good questions. I'm going to wrap it up now. Our Reactor team has been really sweet to let us stay over and answer all these great questions. If you do have more questions, just come on Tuesday, because on Tuesday we're going to have that vision session. And we are going to be, having office hours too. Oh, wait, I do have one bonus demo that I think actually works. I deployed it like last night. Because I don't think we're talking about it this time. Oh, and look, it's even in Spanish. Awesome. So let me see if this is going to work. This is voice rag. Let's see if this is working this morning, because I haven't tested. But what does a product manager do? Oh, you probably aren't going to hear if they answer. Let's see. Oh, it's not even responding. Hello. This is just me being weird and talking to my computer now. Oh, oh, it's not. All right. I think you didn't hear that because it went into my speakers, but it did just reply to me. What does a product manager do? Okay, you can't hear. It's actually being really like this does rag on your data, and so this is something you could check out too. So it's actually doing the real-time voice, but I didn't set up to actually do the proper presentation. Yeah, I know, no audio. I'll figure out audio. Maybe in the office hours I can demo this on Tuesday. It's actually really fun. Okay, all right, so there we go. All done. Just come and join us on Tuesday for our vision session and our office hours, and we'll be doing lots of fun stuff then. Thank you everyone for joining and for such great questions. Bye.
Thank you all for joining, and thanks again to our speakers. This session is part of a series. To register for future shows and watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can find that link on the screen or in the chat. And we'll see you at the next one.